And please take it away, Angelos. Thank you.
Thank you very much, Sam. Thank you also for giving me the opportunity to present in this group my work on variance deduction for Metropolis-Hastings samplers. As Sam mentioned, I'm working as research associate at the MRC Biostatistics unit of the University of Cambridge in the group of Daniela and Angelos. But now I will speak for a work appeared recently in Statistics and Computing Journal, which is joint work with Petros Delaportas and Michalis Titsches. Let's give some setup and some introduction. We are deal here with a discrete time Markov chain denoted by xn, where n denotes the time. We assume that this has an invariant measure pi, and we have also a transitional kernel p. And for a real function capital F defined on the state space, on the same state space as the chain, as our Markov chain, we denote by p f of x this expectation, this one-step expectation here, while pi of f is the expectation of f of x under our invariant measure pi. So this pi of f is usually a target expectation, an expectation that we would like to compute analytically. However, since it is not in the most practical problems, useful problems, is not possible to obtain analytically, we use this estimator based on our samples from the Markov chain to estimate our target pi of f. So we are using this type of ergodic means here, which we denote by mu n of f to estimate pi of f. What we know very well is that we have a Markov chain CLT. We have a central limit theorem for this estimator here. So the CLT says that we have this convergence in distribution for our estimator, and this quantity here, actually this quantity here, converges as n goes to infinity as our samples getting larger and larger, our sample size is getting larger and larger. We have this convergence to the Gaussian distribution for this quantity with zero mean and some variance, asymptotic variance, which we denote by sigma squared f here. So sigma squared f is just, you can think this as this limit, this limiting variance here, the usual asymptotic variance of our estimator. And in the case of our Markov chain, discrete time Markov chain, we can write also this asymptotic variance as this infinite sum here with these covariance terms under the invariant measure pi. What is our aim? Our aim is to improve this usual estimator of our target expectation. So by improving, what we mean is that we would like to reduce the asymptotic variance of our estimator, right? So for this estimator mu n of f, we have this sigma squared f as its asymptotic variance. Our aim here is to reduce the variance for this estimator. And in order to achieve the same, we would like to construct, and we actually construct some functions which are known as control variates, and is a very long technique to reduce the variance even in the simple Monte Carlo case. Okay, and also what we are really interested to do at the end of the day is to reduce the variance using the control variates, the asymptotic variance, but without a lot of effort, without a lot of computational effort, if you want. Let me go briefly to another key object in our research here, in our work, which is the so-called Poisson equation. And what we mean by Poisson equation is this equation here. So for a function f, like our target function here, this function f, we say that a function hat f solves or satisfies the Poisson equation if this equation here is true, right? Where p of f hat is like the one-step expectation that we saw before, this guy here for hat f, and p of f is the target expectation under the invariant measure f. The problem is that it's very hard, it's extremely hard to solve this Poisson equation and to find this solution, this hat f, for continuous state Markov chains. which we're interested in, even in the case that we know pi of f. So think that since we have a Markov chain Monte Carlo set up here, we don't usually know our target f, the expectation. We cannot even calculate our target expectation pi of f. But even if we could, it is extremely hard to solve this equation in the case of a continuous state space Markov chain. But if we assume for a moment that we could solve this equation, okay, so we could find a function hat f that satisfies this equation here, then we could construct a very interesting control variant, this function u, which is given as hat f minus p of hat f. Then we have this function as we can use this function as a control variant. It is a very interesting control variant. First of all, because it has this desirable property for control variants, even in the standard Monte Carlo case where the expectation under the invariant measure is known and actually is equal to 0. And even more importantly, if we calculate the variance under the invariant measure of this function here, which is actually our target function f minus the function u, if you can quickly follow the maths, then we have that this new function has variance which is equal to 0. And then by taking into account that this function u has expectation equal to 0, then we can see also that we have an unbiased, this guy here is an unbiased estimator of our target pi of f. So we have an unbiased, a new estimator, actually, if you can follow, which is this guy here. And this estimator is unbiased and has 0 variance. So this is a game over situation, right? Because what we want at the end of the day, as a statistician at least, is to have an estimator with 0 variance. I think this is kind of ideal, I think. But all these things only in the case an unbiased estimator with 0 variance. All these things happen only in the case that we knew our solution to this Poisson equation. So indeed, then we could stop using this usual estimator and we could construct this new estimator, which would have variance equal to 0. Okay, so our problem is that, as I said, we cannot solve the Poisson equation, and we have to work on that. So our starting point here is a work made by Petros and Yannis Kontogiannis more than 10 years ago, where they worked in the same problem, but for a very specific kind of MCMC sampler, which is the random scan Gibbs sampler. And in the very specific case where f of x is equal to xj, so you can imagine that we have now a target pi, which is d-dimensional, let's say, we have d-dimension, xj, by setting f of x equal to xj means that we are interested in estimating the mean of the jth marginal of the target. And if we also assume that our target pi of x is a d-dimensional multivariate normal density, then in this paper here appeared 10 years ago in series B, they found that the solution of the Poisson equation is one of the most rare cases where the Poisson equation can be solved and the solution hat f looks like this linear combination here. Okay, so what we do in our work is that we try to follow the Laportas and Kontogiannis, and we first try to work to extend the work there and to go beyond the random scan Gibbs sampler, and we try to go to the random walk Metropolis and to Metropolis adjusting Lageva diffusion samplers. We are not so optimistic that to find the exact solution in that case of the Poisson equation, because as I said, it's a very hard problem and we will see the details in a while. So we first aim to find just an approximation G to the true solution hat f for the case of a d-dimensional Gaussian target. So instead of solving explicitly the equation as in the Laportas and Kontogiannis, we just want to have a good approximation to the solution for the Gaussian target. And then by assuming that a d-dimensional Gaussian target can be modified such that it is a good approximation to any general target pi, then when to construct control variates based on this approximation to the solution of the Poisson equation for the Gaussian target. Okay, so let me give a bit more details. Actually, let me give the whole image of the method of our estimator, of our output, and then we can go to the details slide by slide. So let me give the full image first. So let's assume for a while that indeed we have an approximation G to the true solution of the Poisson equation. Then, as we saw before, we can construct a new estimator denoted here by mu n comma g of our function f, which has this form here. And this is this function u in reality, right? This is our control variate constructed from the Poisson equation. But as you may notice here, even if we have this approximation, even if we know, let's say, the solution to the Poisson equation, or if we can approximate well the solution to the Poisson equation, we have the problem that this control variate depends on this one-step expectation here. And this one-step expectation, we can write down the formula and we can see that as main argument, this, as main ingredient, this integral here. And this integral in turn depends on the acceptance ratio of our sampler, which is a Metropolis-Hastings sampler, so has this form here. And this integral tends to be very difficult or even impossible to be calculated for general targets. So even if we know G, even if we have for G, it is very difficult to calculate or even impossible to calculate this integral. And as I said, we want to be here both efficient in terms of error in our estimations and quick in terms of computational time. So what we do is that we propose to estimate this integral, this unknown integral, with a Monte Carlo estimator, the usual Monte Carlo estimator of integrals. But in order to be really fast, really quick, really efficient in terms of computational time, we propose to do this with just one sample size, right? With one sample, so sample size equal to 1. And then we have this formula, this guy here, as an estimator of this integral here. And you can quickly imagine, I guess, that this is indeed a very easy to construct estimator, because in every iteration of our MC sampler, we have a sample from our proposal distribution here, right? This Q is the proposal distribution of our MCMC algorithm. So since we have a sample in every iteration, we can use this sample in order to construct our sample size 1 Monte Carlo estimator of our integral. So we solve the computational time problem. But as I said, we want to be precise here, and we really want this approximation to be to be accurate. And with sample size 1, it's not obvious how to be accurate. And the most usual way to reduce the error in a Monte Carlo estimator is to use control variates. So now we modify again our proposed estimator, which is this guy here, and we add one more term, which we label as static control variate now. And this term aims to reduce the variance of this term here, because this term now, if you notice, if you can see, is a Monte Carlo estimator. So we have, and the Monte Carlo estimator with sample size equal to 1. So we have a lot of variance. So to reduce the variance and keep our method accurate, we propose to construct one more control variate calculated now for each x used to calculate this estimator for each x and each y, which is our static control variate. Okay, so our final estimator depends on two control variates. The one that we call stochastic Poisson control variate, which aims to reduce the variance of our coming from our Markov chain, from our samples from the Markov chain. And then we have another control variant, which we label static control variant, and aims to reduce the variance of our estimator for the stochastic Poisson control variant. I hope everything is clear by now, or if it isn't, just ask any question if you want, because this is indeed our program here, right? This is our method in reality, and then we can see slowly our roadmap, our details. So we can, I will try to go through the details, step by step.
Can I ask a small question about the equation at the bottom on the previous slide?
Yes, please. Sorry?
So down at the bottom. So with the yi, will you have it be the same as the proposal you make in the algorithm, or as part of the Markov chain, or is it sort of generated separately?
No, it's exactly the same one that is used during the MCMC algorithm, the one that you generate in order to accept or reject and put as your sum.
Cool. That's good. And so the reason you can get the static control variant is, I guess, because the Q is going to be Gaussian, essentially.
Yes, and then you will see in the details that we have to choose H such that we can compute this integral here under a Gaussian proposal. We haven't worked with any proposal that is not Gaussian.
Yep, that makes sense. Thank you.
Okay, thank you very much. So if there are no any other questions, let me go to our roadmap here, which is the following. So, as I said, and following the paper that I briefly presented the result before by Alexopoulos and Kotogiannis, what we do here is that we start with the simplest case. And what is the simplest case is that we aim to approximate the solution of the Poisson equation for a Metropolis-Hastings sampler, for a random walk in particular, and for a Mala algorithm, for a standard Gaussian, a univariate standard Gaussian target. Then, in our second step, we try to extend this approximation and modify this approximation to a d-dimensional target. Again, a d-dimensional standard Gaussian target. Our third step is to move a bit more and go to a general d-dimensional Gaussian target, which is not any more standard, but depends on some general mu and some general covariance matrix sigma. And then, as I noted before, by making this assumption that some target pi can be well or less well approximated from a Gaussian target, then we are going to use this approximated solution to the Poisson equation in order to construct control variates, Poisson control variates for any target pi. And then we have to find static control variates to reduce the errors for the Monte Carlo estimator that is used to calculate some of the integrals. And then I will also show to you some of the results that we obtained when we applied all this stuff. Okay, so let's start with our first task, which is how we can find an approximation G to the true solution of the Poisson equation in the case of the univariate standard Gaussian target. So this is in reality the integral equation that we want to solve, okay, which depends on the acceptance ratio of the sampler, halves this difference of the function G, and also here Q is our proposal distribution, which we assume for now that is a Gaussian random walk proposal, and pi of x, as I said, is just a Gaussian standard Gaussian target. So in the Poisson equation, we can delete this term here, which is the expectation under the target, and the expectation under the target is known to be equal to 0. So this is cancelled out. Again, now we are going to use, to start, we use a result from some research conducted by Alexander Magyatovic and Yuri Vongritz back in 2018, where they noticed that this is just a one-dimensional integral equation. So they worked quite a lot to obtain a very accurate numerical solution to this integral equation. So by using their program, we can have a plot, we can have the function G that indeed solves this Poisson equation, right? So we can have the solution of the Poisson equation. And what we did is that we tried to defined explicitly a formula for the function g that can approximate really well the true function, the numerical approximation found by the method by Mijatovic and Vongric. Okay, so what we understood and what we found out, our first, let's say, result or our first assumption, if you want, is that this function g, which is theta times the hyperbolic sine of u of x, really approximates really well the true solution of the Poisson equation in the random walk Metropolis case, as well as in the Mala, right? So in the Mala, again, we can use the program of Mijatovic and Vongric, and we can obtain the numerical approximation, which is plotted as a black solid line here. And then this function, we can modify this function here to also be a very nice approximation for our true solution to the Poisson equation in the univariate case and for a standard Gaussian target. What is really important here is that for this function g, this integral here can be explicitly calculated, right? Because you saw maybe before that this integral is related to this quantity p of g that is needed for the construction of control variate. So this function g allows this calculation of PG, so allows the construction of control variate in the univariate standard Gaussian case. So we are done in this case. Our next step was to go beyond the one-dimensional case, to go in a more interesting case. Let's say that Monte Carlo, or that numerical approximation is not easy to be constructed, for large D especially. So we move to the D-dimensional standard Gaussian target. We fix now our f of x to be x1. So this means that we are interested in estimating the mean of the first marginal of our target. Let's imagine for a while that we have a two-dimensional target now. So we're interested in estimating the mean of the first marginal, but without loss of generality in the terms of we can do the same for estimating the mean of the second marginal or the third and the d marginal if we have the dimensions. P of x is a standard Gaussian target. Sorry, mu here is a typo. This mu is equal to 0 for the time being. So P of x is our d-dimensional standard Gaussian target, and Q is our random walk proposal, okay, with a small step size and the diagonal covariance matrix. What we did is that we extended our G that worked for the univariate case by adding this term, this multiplier here, which is the hyperbolic cosine calculated in the second dimension of the target. Why we did that is that we first studied some of the properties of the true solution of the Poisson equation in the two-dimensional case and also in the d-dimensional case, actually. So we have three important properties for the true solution. So hat f, we know, we have proven that is a knot function. We also know that hat f is invariant to shifts in the y-axis. And we also know that for the particular case of the standard Gaussian target, the d-dimensional standard Gaussian target, hat f is permutation invariant with respect to variables other than x1, where x1 is our target, defines our target expectation here. Okay, so one class of function that satisfies all these properties and also gives nice approximation in the one invariant case is this guy here, right? Which is nothing more than, if you think a bit more, and it's actually written in this way in our paper, is nothing more than a linear combination of exponential functions. Okay, so we make this assumption here. This assumption is convenient because it works very well in the invariant case, also satisfies the properties of the true solution of the Poisson equation in the multivariate case, in the divariate case, and also still and importantly, we can calculate PG, our one-step expectation for this choice of function G. Yeah, for this choice of approximation for the true solution of the Poisson equation. Okay, so now what we have to move to the more standard. So we have up to now an approximation G, we have constructed an approximation G to our, and we can make this approximation quite accurately, accurate by choosing suitably. I can give you the details, but we can make solve an optimization problem to choose nicely these coefficients U2 and U1, and we're going to speak a bit more about this theta here. So we can really construct a nice approximation. You can see this here visually. We can really construct nice approximation for standard Gaussian targets, even in the d-dimensions. Then we had to move in d-dimensional Gaussian targets with general mean and covariance matrix. And what we did is that we proved a small proposition which says that if you have the solution of the Poisson equation or an approximation to the solution of the Poisson equation for a standard Gaussian target, d-dimensional standard Gaussian target, and for this function f, then this function g is your solution or your approximation to the solution to your general Gaussian target with some mean mu and covariance matrix sigma, and this L that appears here is nothing more than the Cholesky factor of the target covariance. Okay, and now, I'm sorry, and now having constructed an approximation to the solution of the Poisson equation for the general Gaussian target, as I mentioned in my introduction, what we do is that we can construct, if we have a general target pi, we can construct a Gaussian approximation to this target by calculating the mean and the covariance matrix of this approximation by employing the MC output. So you can think our method as a post-processing method if you want. So, and making the assumption that this Gaussian approximation is accurate for our target pi, then we also, it's natural to assume that the control variate that we can calculate based on this function g here, because as I said, we can calculate bg, so we can construct control variates for this choice of g, and these control variates, it is reasonable to assume that will be close to the control variates that correspond to the Poisson equation of our target pi, due to this assumption of the approximation of the target pi with a Gaussian distribution. Is it everything clear by now? Or kind of clear? Okay, that's good. Okay, so now since we have our function g, we can construct control variates for the variate Gaussian target. We can construct control variates for any target pi by making this assumption for the Gaussian approximation of the target. And the problem, as I said, is that still for a general target pi, we have to calculate this integral, which we can calculate in the case of a Gaussian target, but for a general target pi, even for the choice, this choice that in the Gaussian case leads to an explicit calculation, in the general case, it does not lead to an explicit calculation, so we have to do an estimation of this integral. As I said in my introduction again, we choose to make this estimation by using a Monte Carlo estimator with sample size equal to 1, and this sample that we need to construct our estimator, our Monte Carlo estimator, comes from the samples that we proposed during our MCMC algorithm. And then we can construct this function. And as I said, in order to reduce the variance of this sample size equal to 1 Monte Carlo estimator, we have to construct a static control variate. And in order this static control variate to make the job, to reduce the variance of our Monte Carlo estimator, has to be well correlated or has to approximate very well the integrand here, right? The function that we have inside the target integral. So indeed, what we do is that we search to find a function h as our static control variate that has two properties. One property is that this h is a very well approximation to this quantity here that appears in the integral. And the second property, as noted earlier by Sam, is that we have to be able to calculate this integral for the particular choice of h. And what we do is that we just say that we can choose our function h to be exactly this function here that we have in the integral, but we replace our acceptance ratio alpha by tilde alpha, which is just the acceptance ratio that we would have if we have a Gaussian target now, right? So now we again use, if you want, the fact that we can approximate our target by Gaussian distribution, and this gives us a very well behaved in terms of correlation with this function here, function h. The better the Gaussian approximation is to the target, the more accurate will be our static control variate. And as I noted several cases previously, for a Gaussian target, we can calculate this integral. So for a Gaussian target, we can calculate the expectation that we need to calculate in order to construct our static control variant. Okay, so I should have convinced you by now that indeed I can construct quite easily without a lot of computational effort my new estimator, so I can replace the usual estimator, which is up to here, right, of my function f, with this new estimator, which has a component that is called stochastic control, Poisson control variate. The component that is a static control variate aims to reduce further the error introduced by this approximation here. One small and final step in our construction is that we have, since we are based on a function g that is not the true solution of the Poisson equation, in order to obtain really a control variate that minimize the variance of our estimator, we have to use a coefficient here, theta, which is calculated from the MCMC output again, which minimizes our variance in the case of this approximation G. Okay, and this theta, it is optimally estimated. It is shown by the Laporte and Kotogiannis how to be optimally estimated from the MCMC sample, so we can just borrow the same construction for this theta that is the usual coefficient in any control variate method, and it is used to minimize indeed the variance. So this is our final version of our modified estimator, and this is the estimator that I use in my experiments below, where I will try to convince you that what we did can be helpful. Any questions? Okay. So let me go quickly to the results, or to some of the results, sorry. So just as a toy example here, I did apply my method, our method, in some standard Gaussian targets. So what you see here in the left-hand side, we have ergodic means for the random walk algorithm, and in the right-hand side, we have ergodic means for the mala. With black solid lines, we have the ergodic means of the usual estimator that we saw in the first slide. And we have each plot here, each one of the four plots corresponds to one of the dimensions indicated by the titles here. So here we have a 2-dimensional standard Gaussian target, a 10-dimensional standard Gaussian target, a 30-dimensional, and 100 dimensions. And the green dotted lines correspond to the ergodic means of our modified estimator, so to these guys here. Okay, so you can see even visually, both in the random walk case and in the mala case, that indeed we can reduce the variance of our ergodic means. Now, going to a bit more interesting examples, I could go, sorry, but I cannot see. Yeah, so, we have something. Okay, so Simon has to leave. Okay, sorry. Yeah, so here we moved to, we measured how much we reduced the variance in our by using our modified estimator. In order to do that, again, in the same example with a standard Gaussian divariate target, where these are the different dimensions, what we did is that we did 100 independent replications of the experiment. So we ran 100 MCMC samplers. We calculated the mean for each output with the usual estimator and with the modified estimator. We calculated the variance in both cases of the estimators across these 100 replications, and we report the ratio of these variances, where in the numerator is the usual estimate, the variance of the usual estimator, and in the denominator is the variance of our modified estimator. So you can see here, for example, that this 93 means that in the two-dimensional case and for the random walk algorithm, our the usual estimator, the usual modified, the usual good means have variance for a Markov chain with 1,000 samples, have variance which is 93 times greater than the variance of our modified estimator. And in the same way, we can interpret all the numbers in these tables here. Okay, so these are the variance, the factors, the estimated factors by which the variance is decreased for standard Gaussian targets in the random walk case for different dimensions and for different sample sizes of the Markov chains for the random walk and the Mala. Moving a bit to more realistic exams, we go to logistic regression exams. So we applied our method in a variety of data sets with several dimensions. So we had small dimensions in these data sets. For example, we had a target with 3 coordinates and 250 samples, whereas in our largest example, in the logistic regression case, we had the target with 25 dimensions, 25 coordinates, and a sample of 1,000. And you can see here again the factors by which our modified estimator, by which the variance of our modified estimator is smaller than the variance of the usual estimator for different sample sizes of the Markov chain and for the different data sets. This range here is across the dimensions of the target. So if I would like to be more accurate, I could report only the lower bound, right? The left hand side number, because the minimum is what is the interesting thing. The maximum is a bit of showing off, but I reported both. So you can see the factors, the range of the factors across the dimensions for random walk and Mala for all these targets here. And we also tried to apply it in even more dimensions. So we went to the well-known, at least in econometrics, stochastic volatility model, where we had capital N observations. And again, we used different Markov chains with different sample sizes, 10,000, 50,000. Capital N here is set it to 100. So we had 100 latent states in the model and 3 parameters, 3 static parameters for those that are a bit familiar with the stochastic volatility model. So at the end, we had capital N plus 3 dimensions, and you can see here the different choices of these. So yeah, sorry, was not only for 100, it was for 50, 100, and 300 dimensions. And this are the sample sizes of the Markov chains, and this our various reduction factors. Okay. And we also applied, and I think this is my final slide with results, and we'll go to the conclusion. We also tried to replicate an experiment made by Mijatovic and Vogels, where our target was a mixture of multivariate Gaussian distribution with this mean here. So this experiment could show us, could evaluate, if you want, our assumption for the departure, for the Gaussian approximation of the target, because for the larger H, the more that we depart from the Gaussian target. So we can, if we want, test our assumption for the Gaussian approximation to the target. And you can see here for 10 dimensions and for 50 dimensions and for several choice of heights, how our method behaves in terms of variance reduction in the case of the random walk Metropolis. We didn't use Mala here because we have a bimodal target, so Mala would be a bit more tricky to converge. So as I said, this was my last slide with results. What we presented here, what I presented was a variance reduction method with negligible cost, I think. So I should have convinced you that indeed the computational time needed to post-process my MCMC samples and construct my variance reduction method is really small. As you may notice, this is easily combined with adaptive MCMC schemes because our proposal distribution was proportional to the proposal covariance matrix was proportional to the covariance matrix of the target. And this is, I think, a very interesting venue of future research because there are still many open problems here. So if you may notice that we had a very particular choice for the function f. So we focused on estimating the mean of the target across any marginal, but we could estimate the variance of the target. We can estimate credible intervals, so indicator functions and things like that. We can try other kernels and go to more useful kernels, which are the Metropolis within Gibbs that people usually do in order to draw samples from realistic target distribution. And we can also play with our G function, with our approximation to the solution of the true solution of the Poisson equation for any given target pi, and many others. So, variance reduction, I think, is a hot topic even now outside of the Markov chain world, where people do variational inference and things like that, and maybe they want to reduce the variance of mean estimators, let's say. So that's all from me. I hope it was a bit of interesting.